Okay, so hello everybody for joining this online flow seminar live in person. The talk is also recorded and later available on YouTube. So this week you have a speaker, Yaodong he's a PhD student at Berkeley, and he has a lot of work on general machine learning, various topics, and this seems to be one of the first paper on federated learning, but it's quite exciting results, and yeah, the floor is yours to now share all what you have. Okay, thanks for joining as a speaker today.
Yeah, thank you for the nice introduction, and thank you for having me for sharing our recent work. Yeah, I'm very excited to share our recent work on some strategy try to convexified approach to tackle some data heterogeneity in federated learning. So this is a joint work with Alex, Pranees, E, and Mike, all from Berkeley. Yeah, and we also have, this is a paper accepted at last year's NeurIPS, and we have a GitHub repo to reproduce some of the results in the paper. Also, before we start, just for the talk, just feel free to interrupt me if you have any questions, anything unclear, I could try to clarify. And yeah, it would be great if the talk is more like interactive. Cool. I will first start with the motivation and also lay out like what's the problem setup for this work. And then I will present the methodology and the experiments. To start, I think I don't need to motivate much in terms of why federated learning is interesting, something like this. So overall, like kind of federated learning is becoming an emerging tool or technique, both in industry and some other places. And compared to, I have been working on like distributed optimization before. I think there's some interesting like differences between federated learning and the distributed optimization. The thing I found might be quite critical in practice for federated learning is that you cannot decide how the data is distributed across different devices. So in distributed optimization, you can try to, probably you can also leverage some algorithms, try to allocate the data like onto different machines, and you can actually speed up the convergence by leveraging or distribute the data more clever. But here you can, because every device is, they cannot share the data to the center, and you cannot decide how the data is distributed. And we also want to minimize the number of rounds for communication, which is quite expensive in the federated learning case. And here is the setup for this work. So it overall is a little bit, it's not like very general to handle or to include all the problems in federated learning. But like I think several components probably could be relaxed for future work, and we can discuss afterwards. So to start with, the setting, the first requirement is we are focusing on the cross-silo scenario instead of cross-device. Basically, we do not have many devices or many clients in this whole federated learning optimization problem. You can think the number of devices is smaller than, let's say, 100. And the second requirement is we have like the full client participation. I guess this could be relaxed later, but we can discuss later. But here, for the simplicity, we just focusing on every round, we can have all the gradients or any updates from all the clients. And the third requirement is we have a single global model. So instead of, in this work, we are not focusing on like some personalization perspective. So we are trying to optimize one single global model for all the clients. And the last requirement or last for the setting is we assume there exists a global model that achieves good performance for all the clients. So for this requirement, you can interpret something like, say I have a very big model or a very big deep neural net. This network, the model capacity is very large and it could generalize pretty well. So after fitting on all the data points from all the clients, it could generalize pretty well for everyone. So that's all the settings set up for this work. So before move to the next slide, any questions, clarifications on the setup? Okay, cool. So yeah, this is the training objective for setting up the problem. So here this is pretty standard in federated learning. So we have an objective L theta, and we are minimizing the weighted sum over from K from 1 to capital K. And the weight for each client is the number of data points divided by the total number of data points from all the clients. So the challenge here is we want to tackle in this paper is mainly due to the dissimilar data distribution. So what do I mean by that? So one kind of scenario is that in the very simple case, we have some label shift from one client to another. For example, in the left figure, in this case, we are considering or visualizing this C410 data set distribution. For the left-hand side, we have, say, 16 clients. For the x-axis, every column represents one client, and for the y-axis is it represents the labels. And the large or the size of the circle for each grade represents how many data points or the ratio of the number of data points from that class divided to the overall samples for that client. We can see that on the left-hand side, we have like kind of every client almost has like all the samples from have samples from all the classes. By the way, this parameter alpha controls how large the data heterogeneity is. So you can interpret this, the larger the alpha, the more similar the data distribution across the clients. And on the, however, on the right-hand figure, we can find that a lot of clients have missed the classes or missed the samples from a lot of like labels. So basically, for example, in this, the client one, it does not have the labels for from the class from 5 to 8. So basically, there's some like label shift across the clients. So this is only one kind of data distribution shift or data heterogeneity in this federated optimization. So just to demonstrate how hard or like how challenging this is, we are like doing some simple experiments to demonstrate like the impact of the data heterogeneity in this for the federated averaging, which is the very standard to-go algorithm in federated learning. The red bar represents the baseline for the centralized version. Like for centralized algorithm, the data heterogeneity doesn't matter because you can think we are pooling the data together and do this SGD optimization. However, for the federated averaging, suppose we decrease our alpha to like from 0.5 to 0.1, say we enlarge the level of data heterogeneity, the test accuracy is dropping like around say 5% plus. To further like make the problem more challenging, we are considering the case that every client only has 2 classes. So basically every client has like samples from say class 0 and class 1. So it's a pretty challenging case. And in this case, the accuracy drop is much larger. And in the extreme like challenging case, very pathological case is every client probably only has 1 class. And in this case, if you just do some local training, you cannot learn anything useful because you are learning like some all-one classifier. You are mapping all your samples to one class. And in this case, like the accuracy is dropping like a lot. And this is like a very simple experiments to demonstrate like how challenging the like a very simple type of distribution shift, this label shift is. Any questions so far?
Yes, I would have one quick one. So what's the setup that you consider here for federated averaging?
Oh,
so
it's
local steps and this one.
Oh, you mean like how many local steps for each between each two communications?
Yes, yes.
Yeah, so here we are considering like the number of clients is 10. And this is the whole CFR10 data set. And for each client, we are using 5 epochs of local training before one communication. Yeah.
So just a question about this. Don't you think that this is also like kind of a, rather than like just, okay, so it's this one, like you could run federated averaging with just one local steps, and
Yeah.
you should get the performance of centralized model. So are you trying to solve here like kind of a communication bottleneck issue?
Yeah, exactly. So yeah, what you said is exactly correct. So in the extreme case, if we make the local training step just one iteration, it will just reduce to say either the GD or the SGD case for the centralized case. But in that case, the number of communications will go up, say, at least a few thousands or like more. Also, by the way, the number of communications we are considering here is within like say 200 number of communication runs. So we will see our later experiments. So for fair comparison, we are also like try to limit the communication runs like to be as small as possible. Okay. Yeah, but that's correct. Like if we do not limit the number of communication runs, this is not a huge problem. Yeah.
Oh, thank you.
Yeah, thanks for the clarification. Cool. So yeah, next I will briefly talk about why this might be challenging. So give a quick intuition is on the left figure, we can see that suppose for client 1 is function is f1 and for client 2 is f2. We know that the averaging of the optima is not the optima of the averaging and average the objective. And this is even the case for like convex. Like even you have convex loss functions, you just naively optimize averaging the optimas, it does not work. And however, luckily we have some gradient correction based approach. I think also several folks from like right now, they are contributing to the algorithms, to the methods I'm showing here. So by leveraging the gradient correction based approach, at least for the convex case, we can probably tackle this, the data heterogeneity can be probably handled by this gradient correction based approach. And we can, in this very nice setup, say strongly convex and smooth setting, we can get linear convergence by using this gradient correction based approach. This is example showing like this scaffold, which is the gradient correction based approach. It could like tackle this data heterogeneity in the convex setting. So here we are now training a neural network. So we are training a linear classification model, and for the orange and red curves, they are representing the federated averaging. And suppose if we switch federated averaging to scaffold, we can get better like test accuracy performance by like using the gradient correction based approach. However, if we switch back to the earlier example, so if we are training a residual neural network, a big like a non-convex deep neural network model. In this case, if we adding this scaffold or trying switching from federated averaging to scaffold, actually it does not work that well like in this non-convex like non-smooth setting. And if we look into the case of the non-convex setting, so compared to the convex case, on the right-hand figure, it's representing the non-convex setting. It's training a residual network with 18 layers. So here we can see for the easy case, when the alpha is 0.1. So both federated averaging and scarfold, they are converging pretty nicely, or at least converging to pretty reasonably good generalization performance here. However, if we switch to the very challenging case, which is the number of classes for each client is 2. Say every client only has 2 classes. In this case, both scarfold and federated averaging suffer from this data heterogeneity case. So overall, we can see from both figures that if you don't have the non-convex model, the data heterogeneity is not a huge problem. And if you don't have the data heterogeneity, if your model is not just non-convex, empirically federated averaging and scarfold are working pretty well. But however, in both cases, both data heterogeneity and non-convexity, current FR algorithms suffer from this data heterogeneity and non-convex issue. So how in this work we are trying to tackle this problem is how to overcome the issue of if both cases happen. And before we move on to the methodology, so any questions, clarifications so far? Okay, cool. So next I will present our proposed approach trying to tackle this this issue of heterogeneity and which named train, convexify, and train, short as TCT. So the first question when we started this project, try to dig into the problem, the question we want to ask is, as we saw before, the federated averaging is not generalizing pretty well in terms of measured by accuracy. But the other question is, what's the quality of the representations learned by these federated learning algorithms? So basically, is the neural network learning something useful in terms of the representation power? And to examine this representation quality, what we did is as follows. So here, just conceptually, we have a multi-layer deep neural network, and every layer in the residual network could also be a block. It's actually a layer. It's kind of one layer could be a block. But here we just, for simplicity, we just consider this multi-layer neural network case. Say for now, it's fully connected. And here, in order to try to examine the quality of the representation, so what we do is we first learn this L layer deep neural network by using the algorithm of federated averaging. And the next step, what we do is we freeze the small L layers and just keep those layers freezed, and those parameters are learned by federated averaging. And what we do is retrain the remaining later layers through the centralized SGD. And to clarify that this algorithm or these steps are not actual federated averaging algorithm, because federated learning algorithm, because it requires the centralized SGD, or at least the number of communications is very large. But we are just using this try to evaluate the quality of the representations. So for to give a better realization is, here we are considering freeze the first 4 layers and just retrain the last layer using centralized SGD. And what we can do, we can also freeze the first 3 layers and retrain the remaining 2. And in the extreme case, if we retrain the whole thing or all the layers, this reduced to the upper baseline of centralized SGD. So there's the federated averaging, the weights are fully removed from this network. So what we did is as follows. So just simply for this residual network experiments we saw before, if we just retrain the last layer, so freeze the first 6 layers, we are reporting like the test accuracy of the retraining after the last layer in this row. So this row represents like the accuracy after the retraining. And just for comparison, like we could replace this federated averaging initialized weights with the random initialized weights. And we just retrain the last layer of the network. And for this column, this random init column, so we are making the first 6 layers, all the weights are randomly initialized. And this is just to compare, for comparing the quality of the federated averaging versus if we just randomly initialize the network weights. So we can see that by just retrain the last linear layer or the last layer, it helps a lot. So it's boosting the accuracy from like below 50 to somewhere close to 80%. However, it's still far from the centralized baseline, so it's still not perfect, but it's boosting a lot. What if we further like train more layers using this centralized SGD? We just fix the first 5 layers and retrain the last 2 layers. We can see we can boost the performance a lot, like by retraining like just one additional layer. And we try this experiments from enlarge the number of layers of retraining from 1 to more, and we can see that when we increasing the number of retraining layers, we can get more like a boost, or we can get continuing like improvements by retraining more layers. And the interesting observation we found here is that the federated averaging is actually learning something very useful. And all the layers of the federated averaging learned models are contain useful information in terms of the representation quality. So any questions so far for this particular experiment? Okay, cool.
Yeah,
so,
I don't know, maybe just very quickly. No, so you say the second column now is this random initialization, and
yeah.
somehow it's also surprisingly good to know if it. But okay, you basically train 6 out of the 7 layers, and then you get a good. But this means.
This means
okay,
that
so just the first layer is random, and.
Yes, exactly.
Probably
so
not
the first.
needed.
Yeah, I think the first layer you can think in this case is more like a convolution layer. Like it's just the 3 by 3 convolutions. It's not like that essential. Yeah, your point is very interesting. So I think even in this case, if the first 4 layers are frozen by random weights, it's still learning something useful here. I think this is still better than the like very worst case, or the baseline of federated average. Yeah. Cool.
No, I think very good. Okay, thanks.
Yeah, thanks for the question. Cool. So based on our observation, say we know now we have the information that federated averaging is learning something useful. So how can we leverage this fact and design something, some other algorithms could tackle this data heterogeneity issue? Because the previous experiments is not actually a FR algorithm, it's just to try to, it requires a lot of number of communications. So in this case, on the left column, by using the federated averaging, we can learn something useful in terms of the representation by using the non-convex laws. And suppose we just freeze everything and the previous SGD centralized retraining is kind of a non-convex procedure. It's still using SGD to optimize a non-convex loss. So what if we can convexify the model we learned by this federated averaging and convexify through some procedure? And in the second stage, instead of solving a non-convex loss, or minimizing a non-convex loss, we are minimizing a convex loss, say through this gradient correction-based approach. Because as we mentioned earlier, like once you have this convexity, there's a lot of nice things you can do. But if the problem is non-convex, like we don't have that many tools to have the theoretical guarantees to tackle this data heterogeneity issue. And this convexify approach we take in this paper is through this ENTK, which means the empirical neurotangent kernel representation. And so here I just give a very quick intro to how to compute this empirical neurotangent kernel representation. So you can interpret this f x theta. So x is our input, theta is our optimized, like to say the federated learning, federated averaging optimized parameters. And f is mapping this input through this network to get the output. And we can decompose or like approximate this function output by doing the Taylor expansion, just to expand to the first term. And then we have this empirical neurotangent feature vector. And this vector is the ENTK representation we are referring before. And there's some techniques or details in terms of how to compute this ENTK more efficiently. And you can refer to our paper for a bit more details in terms of how to compute this very huge vector. And the next question is why ENTK is the good choice to go, or why don't we use some other kind of approach to convexify this whole procedure? So this is a very nice work from this one of the collaborators of this paper, Alex Wei. Alex has a pretty nice paper last year in ISML. They are trying to look into the ENTK representations and compare the ENTK versus the fine tuning versus the last layer retraining. And they found that actually ENTK could approximate the fine tuning pretty well in terms of the final accuracy. And say here, if you just do the last layer retraining, there's still a pretty large gap between the fine tuning versus last layer training. But if you use the ENTK representation, the gap is much smaller. And to note that here, the network is ImageNet pre-trained model. So if you're using a randomly initialized model, the ENTK is not very effective. So overall, like the high level to go message is ENTK representations are pretty, can be interpreted as a good proxy for this to approximate the fine tuning. And overall, it's still like a convex problem. You can have, in the centralized case, you can have kernel tricks to compute the solution very efficiently. Yeah, for more details, please go to Alex's work for more details of very interesting findings regarding the ENTK. And after this very quick intro to how to compute ENTK, let's look into how to convert or convexify the model through this ENTK representation. So actually, it's very simple. So after we get this federated averaging optimized network, we have those parameters, and with that parameter and for each data point, we could obtain the ENTK features for each data point from every client. And after having these ENTK vectors, or this huge representation vectors, what we solve in the second stage, we are solving an overparameterized linear regression problem. So here we are converting this every label to a one-hot label vector, and we are using the features as the ENTK representation vectors. And then we are optimizing one linear model across all the clients to solve this overparameterized linear regression problem. And to make the predictions, just to take this linear model, this regression model, you have a say a k or 10-dimensional vector, and then you take the max, and that's your classification prediction. So any questions so far, like regarding how to transform the previous problem to this over parameterized linear regression problem?
Yeah, maybe just a bit on clarification. So can you comment on the dimension of this ENTK vector? So I mean, does it depend on the data set size or on the classifier output, or just that we have a maybe a bit better picture of what?
Yeah, exactly. Yeah, that's a very nice, good question. So here, so based on the very the basic calculation of the ENTK vector, the dimension should be at least the same number of parameter, the number of parameters of the model. So if you have like the residual network have say 5 million parameters, so this ENTK vector is 5 million for each data point. But later we found that just to do some random subsampling, say we are not using the huge vector, we are doing the subsampling from this huge vector, it still works pretty well. But if you use the without the subsampling, the number of dimension of this vector is the same as the number of parameters of the network.
Yeah. Okay. Thanks.
Okay.
So this W matrix that you're now learning, that this would have increased dimension. But you conquer it by doing first dimensionality reduction so that you don't blow up too much the number of parameters.
Yes, exactly.
Okay,
so
thanks for the clarification.
Yes, just further elaborate on this a little bit. So if we don't do the subsampling or dimension reduction technique for our approach, so this W matrix, if we are communicating this W matrix to across all the clients, the number of parameters we are communicating across the clients is, say, enlarged by the number of the classes for this problem. Say if because the number of dimensions for this W matrix is D by K, and K is the number of classes and D is the original model parameter size. Yeah, that's a very good question. And we could tackle this communication problem. Actually, we can speed up or save the number of communication bits by doing this data dimension reduction. Thanks for the question. Okay, and here is the pipeline for computing this TZT procedure. So you can interpret the first line as we are using federated averaging to learn a federated averaging model, theta. And by leveraging this theta fed averaging for each client, they can compute their own like neurotangent kernel representations locally. Because they have the parameters of the theta, they can use the theta to compute the ENTK features. And by using this ENTK features, we are solving an over-parameterized linear regression model by using the scaffold to solve this W matrix. And the first train is non-convex, and we convexify the model through ENTK. And the last step is training a convex model. And here is the description for the whole algorithm. As Sebastian asked earlier, in terms of the dimensions, we found that after computing the ENTK representations, we can do this subsampling procedure, just randomly take the features from this huge feature vector, and we found that it has very similar performance compared to if you use all the features from this huge vector. And the first stage is non-convex. We train this using federated averaging and extract the features, and then we learn this over-parameterized linear regression model. Okay, so before we move to the experiments, any questions regarding the methodology? Okay, and let's see some results of this new approach. So recall that as we saw earlier, that if we increase the data heterogeneity, the federated averaging and SCARFo suffer from this data heterogeneity issue. By switching this to TCT, except for the very pathological case, we can close the gap a lot, or like approach the centralize the baseline a lot by using TCT. Also to note that the number of communication rounds here is 200 for all the methods. And so interestingly, even for the very hard case, say the very pathological case, every client only has one class. We still learn something like useful, like not that useful, but have 50%. And this is actually slightly better than linear classification. So if you don't learn any features, just use the original feature vector, learn this linear model is below or approximately 45%. So to summary, like even in this very worst case, the federated averaging is learning some representation is useful, and we can leverage that fact by like boost the model performance. And next, this is a big comparison table to compare with some previous approaches. We also have more comparisons in our appendix. So here, compared to 3 popular approaches in the literature, federated averaging, FedProx, and the SCARFo, in different settings, we have like improved the performance a lot, like by a large margin compared to previous approaches. And interestingly, for the CFAR 100, we are maintaining very good performance across a wide range of data heterogeneity level. So to further elaborate on that, this is a comparison on CFAR 100. We are considering 3 different types of, or 3 levels of data heterogeneity here. We're increasing the data heterogeneity level by decreasing the alpha parameter. So we found that for TCT, no matter what the alpha is converging or achieving similar performance, like regardless of the data heterogeneity. But for federated averaging and SCARFo, if the level of data heterogeneity is increasing, the performance is dropping like 10% plus. So this is very interesting, or to show that we kind of tackle this data heterogeneity issue pretty nicely in this. Also for the CFAR 100, the number of classes is very large. In this case, even though the data heterogeneity level is very large, but every client still has, say, a bunch of labels from different classes. It still can learn something useful in terms of the representation. And we also investigate like different components of TCT, try to better understand like which part is effective, or whether we are leveraging some good facts of the convex model. Here we are investigating whether doing local steps is better than like doing one local step. Here the baseline is instead of doing a SCARFo, we can compute the full gradient across all the clients, and one communication round corresponding to say one gradient step. This is there's no local steps here. You're just computing the gradient and aggregating, doing one gradient step. And different curves corresponding to like different learning rate. We are trying to optimize for the best learning rate for GD. And in this case, if we increase the M represents the number of local steps for TCT, and we can find that by increasing the number of local steps, we can like get much better convergence rate, or empirically compared to the using the gradient descent approach. So to summary, like we can leverage the local computation, do more local steps, and converging much faster. And the next, we also compare whether the gradient correction is kind of useful in this case. So to compare this, we switch the second stage SCARFo to the federated averaging. And in this case, we are using 3 different local steps for each methodology. And we found that by using the gradient correction, the gradient correction corresponds to the blue lines. And we can found using the gradient correction can help the convergence a lot compared to like naively doing local steps and do averaging without gradient correction. Sorry. And the next experiments we look into is how many iterations or how many communication rounds we need in order to obtain good representations. Recall that we have 2 phases. The first phase, we are using federated averaging to learn a model. And after that, we do this convexifying and learn a linear model. And in this case, suppose we just randomly initialize network and not doing any feature learning using federated averaging. Actually, the performance is very bad in terms of generalization. Although this training accuracy is approaching to 100 because the model is over parameterized, but without any feature learning, the ENTK is not a very useful proxy for optimizing this problem. But once we have some sort of feature learning, say the number of rounds for the federated averaging for phase 1 is say 20. So we have pretty good like generalization performance after 20 rounds of in the phase 1. And after phase 1 in phase 2, we can get pretty good performance. And we further increase the number of rounds for the phase 1, and we can see it's approaching or is stabilizing at the end. So to summarize, you don't need many iterations or communication rounds to get good like representation performance. So you just need several or smaller than 100 rounds of communications to get the good representations. And here is a more like a direct comparison between TCT versus previous approach. So the transition point is, say, at this point, is switching from federated averaging to the second phase. And we can see that the convergence is pretty fast for the second stage. So say within 20 or 30 number of communication rounds, the model is converging to 100 training accuracy. So overall, it's converging pretty fast in second stage. And the last experiment we considered is what if we have a pre-trained model? So all the previous experiments we are considering, like we are training a model from scratch. We are learning the representations using Fed averaging. And here, suppose we initialized with a network pre-trained on ImageNet. So here is the ResNet 18 pre-trained on ImageNet. And we found that by using a pre-trained model, you can handle or deal with the data heterogeneity or improve the performance by using a pre-trained model. Even for federated averaging and scaffold, the performance is boosted. And on par, or like to compare, after using the pre-trained model, and if we try this TCT, is actually boosting the performance a lot. So it's nearly closed the gap between the centralized versus the non-centralized case. So overall, we can also leverage the pre-trained model as the initialization and further close the gap between data heterogeneity versus the similar data case. Okay, so that's all for the experiments. Any questions for the experiments? Okay, so yeah, here is the very last slides for this talk. So there's a lot of interesting questions after we done this. So as I mentioned earlier, we restrict ourselves into this cross-silo full participation of those scenarios. So there's a lot of extensions can be done in this case. So I think a very interesting question we also want to understand is why the federated averaging is learning something useful. So I think very simple, we know that there's some existing literature have some, I think, low rank or some linear features, try to understand the feature learning phase. But it's also interesting to investigate. So what if simple, what's the mental picture, or if there's some ReLU activation, can we better understand this non-convex model? Why is learning something useful in terms of the representations? And some other questions could be like, what if we switch to the cross device, or switch to the, instead of not requiring the full participation, we just randomly sample the clients every communication round, and what happens in that case. So to summary, like this kind of simple approach is a pretty interesting or effective approach, and it could be a good recipe to convexify your problem and boost your performance, like whatever the first phase is. Okay, and that concludes my talk. Yeah, thanks.
Owen, okay, thank you very much for this interesting talk. So we have a bit of time for discussion. And so please, if anybody of the audience has a question, please raise your hand, or because probably you can also just unmute yourself and directly ask. And while everybody is thinking for something, I mean, I want to go back on this. It's a bit related to this question on the dimension. No, I mean, can you comment a bit on let's say the computational complexity? I mean, you present your algorithm and say, oh, this is like a maybe general recipe to make our problems no convex. But what in terms of computation, what do you have to spend now locally on every device, or do we need to communicate more or less in these rounds? I mean, just can you explain a bit more maybe on the
Yeah, that's a very good question. Yeah, so let me try to elaborate this more. So here, the first phase is as the communication or the computation is similar as before. And for the second stage, or for the feature extraction stage, for every data point is essentially similar as like just do for one data point to get the ENTK representation is similar as one backpropagation for each data point. So you need to spend some computations for this stage, but essentially it's just one backpropagation for each data point. And after this, in practice, we found that just reducing the number of dimensions by like, we can actually reduce the dimension by reduce to the 10% number of parameters for this ENTK representation. So you can interpret this as, say, we have like much less dimensions as the original model. So here in this stage, the number of bits commute to the center is no worse than the first stage. And the actual or the additional computation happens in our approach is you need to do one additional backpropagation for each data point locally. Although the second stage, this does not involve like the communication, it requires a bit more computation locally to get its ENTK features. And to further like clarify the computation or the dimensions for our experiments, say for the CFR 100 or CFR 10, we are using 0.1 million parameters for the ENTK features. And it's much less number of parameters than this whole model. So which means that we are using this subsampling procedure, and we are so basically we are using, if I recall correctly, we are using 1% of the number of parameters. We just sample 1% of the features from this huge vector. So, and it's also working pretty well in practice. I'm not sure whether that answers the question.
No, okay, thank you very much. No, I think it answers pretty well. No, it's saying it's not like, oh, very theoretical and you have a huge overhead, but you say, oh, you can actually keep the overhead quite small. No, it's just maybe one extra pass, but then you get a lot of speed up. So it's it seems quite
quite
usable, not directly. Yeah, okay.
Yes. It's also like there are also some tools to computing the individual, so the per sample gradient. I think some tools from the differential privacy community, because there they need to compute the per sample gradient before the clipping. And there's some tools called Opcus in Torch. You can leverage that tool to compute the per sample gradient pretty fast. Like instead of compute the gradient one by one, you can compute the gradient pretty fast. Yeah. Cool.
Yeah.
Any
But there
other
do
questions?
not seem to be many questions in the in the chat, so I don't know. So
yeah, hopefully
how do you think? I mean, no. I mean, I think it's I don't know. It's just I think all good. But how would you maybe go exactly? Say maybe beyond this cross silo setting. So let's say you just maybe do for the pre-training, you see only a fraction of all the clients. No, so how would you maybe go? Do you think this might still work, or you need to see everybody, or what is your thought on this?
Yeah, I think for the cross, are you like referring to the cross device setting? Say every round
Exactly,
we just sample a bunch. Yeah. I think
exactly.
I think in that case there could be like two scenarios. I think a very extreme scenario is this client only participates for one round and it just dropped from online. And in that case, I think probably it's better to just do one round of averaging over the models and just to give it give the user as like the current copy or current round of averaging. Say for this round, we only have 5 clients participate in this communication. We can have simple averaging over the 5 clients and return the average, the model to every client. And that's a very extreme setting. And for the less challenging setting, so every round we can sample this, we can randomly sample clients from all the clients, and next round we can also sample like a bunch of clients. And in this case, because this problem is a kind of convex, it's also semi strongly convex. It satisfies the I think the similar strongly convex property. And in this case, we can. I think there are some existing techniques to handle this, to try to solve this strongly convex problem by subsample the clients. So basically, in this cross-device setting, once you have the good ENDK representations, I think the client sampling is not a huge issue in this case. I think the very challenging case is if I'm a client, I just participate. I'm participating for one round and I drop offline, and that's the very challenging case. The model might not converge. But the nice thing of the convexity is in the convex setting, if we recall, like 10 years ago, there's a lot of literature on the one round of communication for distributed optimization. In that case, you can actually, by doing one round of averaging or more clever averaging, you can get minimax rate in that case. I think that's also a pretty interesting question. So in the extreme case, one round of communication, you can also clustering your clients and do some clustering based, you just averaging over those clients and they can get better models for their local data. I think, yeah, probably I'm saying too much about that. Yeah.
No, okay. Thanks for your answer. So there's one question from the audience. So Ahmad would like to ask. Yeah.
Yes. First of all, thank you for the talk. And so my question is, I understood that ENTK is computed based on the number of the model parameters for each data point, right? And
yes.
First of all, is it computed on the global model or computed on the local model?
Okay, yeah, that's a pretty good question. So it's is computed locally. So imagine in every communication iteration, you can get a average the global copy for every client. And you are using that like global model. Say I'm a client, I'm using that global model to compute the ENTK locally. So all the ENTK computation is happening locally on every device. And every client is now sending or communicating their local ENTK vectors to the center. They're just communicating the, like, say, the linear model parameters to the center.
Okay, yeah.
Yeah, but I saw a question in the chat. I think this is definitely leaking the privacy. So I could imagine there should be some attacks could reconstruct some inputs or do membership inference attack for every client. I think that's definitely doable. I think we are also working on some privacy version of this TCT because here we don't have any privacy guarantee for now. It's more like a baby step to tackle this the overall problem. Yeah, that's a very good question.
Thank you.
Yeah, thanks.
Yeah, maybe I would have one quick question. Yeah, sorry, this is my Zoom crashed, so I hope this is not like a repeated question. So is there actually any kind of approximation error that you pay for running your algorithm that is irreducible? Because for instance, like if you would run like Fed averaging and you have infinity number of communication rounds, you would eventually solve the problem because you can run kind of a centralized algorithm. Is there actually the approximation error that you can't reduce for your algorithm, or no?
Sorry, Samuel, can you repeat the last part? I kind of I understand the first part. Say if we do not restrict the number of communication rounds, the federated averaging can solve the whole problem. And for our problem, what's the?
So the thing is, because you do this convexification, right? But that's only the approximation, right? If I got it correctly. So is there actually like the approximation error that kind of prevents you from solving the original problem exactly because of the procedure you do?
Yeah, that's a very good question. So overall, our takeaway for this one is, so I think probably this is sort of related to your question. I think we need, so the overall message could be, once you do this convexifization, you are not learning any new features from the model. So you can interpret as, if we doing federated averaging or centralized SGD for the non-convex model, we are learning something useful, like learning useful representations. But once we convexify model and extract the ENTK features, yes, we are like stopping learning new features. We are just learning the classifier. And there is a like gap between this. I guess you're definitely making sense. Like in this case, we are definitely converging to 100 training accuracy, but the generalization is still like there's a gap between this challenging case and alpha equals 0.1. And if we do not limit the rounds of communication for federated averaging, it will converge to the very like ideal solution. Yes, there is still a approximation gap between our approach versus centralized SGD. And that is also something we are pretty interested in. Say, can we combine this TCT approach? Can we learn the classifier, and then probably we can also incorporate the feature learning in at some stage? Yeah, but that's a very good question.
Yeah, thank you, and also thank you for a very nice talk.